Thank you very much, Hugh. And thank you to all of you for coming out today. It's so nice to be here. My commute to Pepperwood, I go up and down Highway 12. I live in Sonoma, and Pepperwood I get to via Calistoga Road. So it's only about half an hour from here. I'll tell you more about it. It's above Safari West, if you know where Safari West is. So today I'm going to give you a lot of information. And to start with, I'll say if I use a term or somehow use an acronym that you don't know what the heck I mean by that, please raise your hand and just ask for clarification, because I don't want to lose you in the process. But we're going to have a lot of time for questions at the end of the presentation. So if you have a substantive question, we'll hold it till then. So today I'm going to introduce Pepperwood to you, tell you a little bit about the amazing preserve and all the activities we have going on there. And I'm going to tell you a little bit about myself and how I got interested in the field of climate adaptation. I'm going to talk a little bit about the difference between climate mitigation and climate adaptation. Those are two different things that we'll define. And I'm learning as I do and more of these community presentations to undo my scientific training. So I'm going to actually tell you the answer at the beginning of my presentation and then show you why I've come to those conclusions. But we're going to dive pretty deep into some science today. I've got graphs, I've got maps, I'll walk you through them. And like I said, if you have questions, let me know. And then talk about how we're using the science to make our region prepared for the climate change that is coming. And that's really my passion, is to make sure that my local community has the very best science to use in making decisions. And luckily, we live in a place where the people who are managing our water and our land and our public safety are very, very eager to be at the cutting edge of that. And I don't know if you know that Sonoma County was the first county in America to set goals for reducing greenhouse gases. And we're now being recognized as a climate champion by the President's Office on Climate. We are recognized as climate champions because of the work I'm sharing today. And then we'll talk more about why we're so glad we live here, where we have this kind of local leadership going on, and then lots of time for questions. So if you haven't had a chance to visit Pepperwood, please come. We have this incredible reserve of 3,200 acres that's protected as forever wild. And then in 2010, we opened this new Dwight Center for Conservation Science. It's a 9,400 square foot LEED certified facility. It's a green building. And this is where we have all of our educational activities and the scientific research activities and the community forums that you can find out about. So our goal is to work on solutions to help protect our land and our water and our wildlife. There's a lot of ecology institutes in the Bay Area focused on the Bay. The San Francisco Estuary Institute, the Bay Institute. But Pepperwood is one of the first institutes using science to think about the rest of the Bay Area, the land that we live in, Sonoma Valley and Napa Valley, and the beautiful mountains and streams and freshwater resources that people and critters call home. So our mission is advancing science-based conservation throughout our region and beyond. So we do a lot of work right directly on the preserve to show people how to take care of the land, but the work I'm showing you today is part of the regional work we do to think about Northern California as a whole and how to apply those lessons throughout the area. I want to recognize our founders, Herb and Jane Dwight. Does anyone know the Dwights? They live up in Healdsburg. There you go. So Herb was the founder of Spectra Physics in 1969. It was the first Silicon Valley company traded on the New York Stock Exchange. Previously, he was at Hewlett-Packard, and I don't know what they were thinking, but they let him take the laser patents and start his own laser company. So it was also the first laser company in America. That company was very successful. Herb and Jane moved up to Healdsburg about 20 years ago, and they fell in love with the land at Pepperwood, which belonged to the California Academy of Sciences. And their vision was, how can we make this land accessible to our community and to our children to learn about science? And so we have them to thank for giving the preserve to the community and financing the construction of this incredible facility, which we call the Dwight Center for Conservation Science. So this is a map of the property. It was assembled by Ken Bechtel of the Bechtel Corporation. He fell in love with this area and started buying up parcels, and he ended up with 7,500 acres. He donated this portion to the California Academy of Sciences, where he was a trustee. He was also the president of the Boy Scouts of America, so he had a real passion for getting youth into the outdoors. And then this other side of the other 3,200 acres, which would be up here, are still farmed by his family. It's called Knights Valley Ranch, and you get there through Knights Valley. But all these different colors on the map are showing you all the different vegetation types that we have at Pepperwood. We have 750 different plants that have been documented at Pepperwood. So when it comes to biodiversity, we're a real sample of the incredible biodiversity of Northern California, which is one of what they call a biodiverse hotspot on the globe as a whole. So the yellow is our open grasslands. The lighter blue is our oak woodlands. We've got Doug fir forest. This is a redwood forest, tiny patch. The purple is the scrubby chaparral. So we can really understand all the different habitats in our area. And this is the Dwight Center, and this is about a 5-mile-long ridge of the Mayacamas Mountains that we take care of and protect. So I think of Pepperwood as a living laboratory where we can do the scientific work to explain how healthy is our land and what can we do to help make it healthier. We have kids coming all year round. So we serve all the elementary schools within a commuting distance in both Sonoma and Napa County, 1st through 5th grade, bilingual programming that reinforces the science standards. The kids spend 3 visits with us over the course of the year. They have a nature journal, and we ask them to develop their own questions and to go collect the evidence to explore those questions. If you're following where education is going in California, the new science standards for kids is all about inquiry. We're not trying to teach them to memorize something from a textbook. We're teaching them how to do science. We have an award-winning teen program that we just started 2 years ago called Teen Nat. This is an internship program over the summer where we treat the kids as interns who are working for us. They collect biodiversity data on the preserve. They learn how to use the technology, the mapping technology, how to photograph things, and they upload that into a worldwide database. And some of the work, this gal is actually monitoring that little patch of redwood forest, which is a project we're doing with Save the Redwoods. So we're helping them get data for their statewide work. And then finally, we have terrific programs for adults and families. And you can find out about those through our website. They're also listed with the Santa Rosa Junior College Bulletin, because we've been a partner of the junior colleges for some time. And these folks are doing a weekend workshop in nature journaling with one of our leading experts on documenting nature. This is Jack Law Muirs, who's the author of all the field guides. If you go get a current field guide for this area, Jack is the one who made it. So terrific programs. And then we also have incredible volunteers who donate over 7,000 hours a year helping us do the scientific work and the land restoration work that we do. So I have to say much of what you're going to hear about today is in thanks to our volunteers, and they're key to how Pepperwood fulfills its mission. So just a pitch, it's wildflower season coming up around the bend. We are offering extended wildflower hikes this year. And April 26th, we'll have a wildflower open house where you could come visit the preserve, see what we're up to, take a hike, take a picnic. We're also going to be featuring a WAPO basketry exhibit at that time. We have a Native American council that advises us, and we'll be featuring the arts of the WAPO, who are not a very well-known tribe in the area. So come visit us, and there's information about Pepperwood in the back. I brought my annual report. It's very easy to find us on the web and sign up. You get an e-newsletter once a month, and you'll find out everything that's happening. So research, education, and community coming together to take care of this place that we love. So what I'm going to talk about today is a challenge that really was deeply personal based on the work that I was doing in this area. And that question is, how will a changing climate affect the lives and the landscapes of Northern California? And how can we, as the stewards of the land, make our working lands and our protected areas healthy and resilient in the face of this change? And one of the things we do at Pepperwood is we get to put together teams to answer questions like this. So the work I'm sharing today, and you'll see a picture in a second, is really a bunch of scientists that we got to cherry pick and put together on this team. My own background is that I'm a hydrologist and a fluvial geomorphologist. Many people love that word. So fluvial, flowing water, or like fleuve, the river in Latin. And then geomorphology is studying how the water shapes the land. So when I was a little girl and I got to go up in an airplane for the first time, I was just glued to that window looking at the surface of the land and starting to wonder, what's making those patterns? Look at the river. Look how it meanders. What are the laws of physics that help to guide this? I was telling Hugh that my first job out of college, I was at the San Francisco office of the Environmental Protection Agency, and I became involved with their wetlands protection program, and I got really interested in how can we restore rivers and wetlands that have been damaged. Many of the projects I worked on, there had been big gravel mines digging out the river. How can we put the river back? And what I learned while I was at the EPA is that our ecologists and our biologists knew what plants they wanted to grow there. They knew what animals they wanted to live there, but they didn't really understand the physics of how the water and the earth would combine to create those habitats. So that became my area of interest. And I went back to school at Cal to get a PhD in that. And for the first 15 years that I was out of my graduate program, I worked on river restoration programs. So I was the restoration program manager for Sonoma Ecology Center here in Sonoma Valley, and I worked with 800 streamside landowners to help them plant trees next to Sonoma Creek and the tributaries of Sonoma Creek. I got to walk all those creeks. I did a study on how we could improve fishery habitat, and many of those projects are happening now, like the Stewart Creek culvert removal project. I also started working half my time in Napa Valley, and I worked directly for 30 vintners and growers on the Napa River, designing a project with them to protect the vineyards from erosion, but then restore fish habitat. I handed that project to a dear friend of mine, and I have to say it's almost done being constructed right now. That's 11 miles of habitat restoration on the Napa. And as soon as we created the habitat structures for the fish started coming. So these are the kinds of successes that I was so passionate about. But my interest in the climate started when I was working on the Napa River. And I take my work very seriously as a public service. And we had designed this project the way that I was taught to design at school, which is we looked at the 100 years of history on the Napa River, and we designed the project to suit the historic conditions. And yet, in the scientific community, it was 2007, the news was in. Our climate was already starting to change. And 100 years from now, it could be quite different than it was today, and especially than it was 100 years ago. So I started really having this conscience problem of raising millions of dollars, both from the farmers and from the state of California, to build this project. And to do our due diligence, I think we have to start to think about designing these projects to be resilient under climate change. The problem was there wasn't any information at a scale that I could use. I'm going to show you what the state of the science was at that time. What is it now, 6 years ago? And it was just too broad scale. Northern California was one big summary, and that wasn't going to help me on the Napa River. So that's really what started this journey, was wanting to get information that people like me working on the ground, trying to help our environment, could use to make good long-term planning decisions. So here's some of the take-home messages. And some of this may sound obvious, but it actually takes a lot of scientific work to feel confident about this. But the future of Northern California is going to be more arid. I'm going to show you that there's a lot of uncertainty about how much rain we're going to get and how we're going to get that rain. But I'm here to tell you that if climate change causes it to be a lot rainier here, it's still going to be more arid at the end of the season. Because the way our systems work, we have that long, dry summer. If that long, dry summer is getting hotter and hotter, we evaporate the water out of the land. So this is actually a pretty important discovery that my group made, because up till then we didn't know if it was going to be drier or wetter. And we can say conclusively it's going to be more arid. And the area here, when you look at the future models, it's going to be more like Santa Barbara inland, okay? We've all been down to Santa Barbara. They've got a milder climate. That's what we're headed for. Now things could be worse, right? I love Santa Barbara. But that transition from what our climate is now to Santa Barbara is what we're thinking about. How are we going to weather that transition. So we have to rethink our conservation goals. So in my work of trying to protect these animals and these plants in our water supply, up till now, Pepperwood Preserve, even the name Preserve, we're going to keep it the same. We're going to keep everything the same. It's going to be just like this for generations to come. The Wilderness Act of the U.S. Congress, which we just celebrated 50 years, that's what the language is, to preserve and to keep things the same. This is kind of a revolution for people in my field. That's just probably not very realistic. So we have to be more open to how do we manage a dynamically changing system, and how do we set targets? Because for Pepperwood, I have targets. So it may not be realistic to say I want exactly the same trees growing there, but maybe it's realistic for me to say, okay, well, I want there to be native trees, and whatever is the native vegetation that is going to be suitable, that's what we want to help establish. And then finally, and it's interesting, I was just interviewed by a graduate student who works at the national and state scale. And I had to remind her, local communities are the ones who are in charge of their water and their land. And when we talk about climate adaptation and taking care of our water and land, those are local decisions. Those are local decisions that local government agencies make, that you guys make as private landowners, that you make when you decide what to do with Oakmont as a community. So this is where the leadership is going to come on these issues, and this is where the decisions are going to be made. This is where the rubber hits the road. And that's why I'm so proud of Sonoma County for helping to show other local governments how to do that, because I think all of you know global climate change is a global phenomenon, and I think when we think about global problems, it gets very overwhelming. But when we realize we have the power locally to take action, it puts us back into a position where we can not be paralyzed, but think about how to move forward. So mitigation versus adaptation. Fasten your seatbelts, here come the graphs. This comes from the Intergovernmental Panel on Climate Change. Have people heard of the Intergovernmental Panel on Climate Change? They call it the IPCC, right? Yeah. This is really a remarkable thing, okay? We have 200 world experts who had to get in a room and come up with a consensus. Now, I got to tell you, I work with scientists. Getting them to agree is not easy. But this is how important this problem is to the world scientists, that they made the effort. And by the way, they are volunteers. They volunteer their time. They do not get paid. And they issue these big reports. So a big IPCC report came out in 2007. That was the one that made me realize, wow, climate change is here and it's happening. 2013, a new assessment came out. So this is a graph from that assessment, and it's showing you temperature, global temperature across the whole planet, and the trajectory that we've been on. We've had this is all degrees Celsius. I'm in the process of turning everything into Fahrenheit. But 1 degree Celsius is about almost 2 degrees Fahrenheit. We've already experienced this change. This is measured globally. Let's see if I can get this thing to work. So the question is, what kind of a trajectory are we on moving forward? So this bottom here is cumulative CO2 emissions, okay, the major greenhouse gas that we're working with. So this is a very well-established relationship that as we put more CO2 emissions, this is gigatons of carbon, into the atmosphere, we're on this trajectory of warming up. So when I talk about climate mitigation, it's tackling this problem. Climate mitigation is the work that people are doing to reduce these CO2 emissions, to get to the root of the problem and help turn this around such that perhaps will be on the lower end of this range down here, which is the more optimistic range, as opposed to being here in this higher range rate of emissions. So that is what mitigation is about. It's about getting us off of fossil fuels, reducing the rate at which we're putting CO2 in the atmosphere, so that this driver of change is reduced. Now, adaptation is dealing with this part of the equation. You know what? Things are changing. We need to adapt no matter what. We're not giving up on mitigation, but the adaptation question is, how do we adjust and prepare for this inevitable transition? Because I have to tell you, even if we just stopped emitting carbon today, it would take about another 100 years before this situation would level out. So we're committed to getting warmer to some extent. And we're also committed to trying to slow that rate. But for the rest of the talk, I'm going to be talking about adaptation, not the mitigation side of the equation. This slide is supposed to help simplify the situation of models, so I'm going to walk you through it. Here is radiative forcing in watts per meter squared. This is the amount of heat that we're generating in the atmosphere. This is so as you go up here, it's getting hotter, hotter, hotter. And then here is now the timeline over time. So when I talk about turning off everything that burns carbon and getting us to stop all of our emissions, this is this line right here, right? It warms up, and then we get our act together, and it tapers off. I call this the super mitigated scenario. Super duper mitigated, like we've got a carbon vacuum in the atmosphere. This here is, if you read Al Gore's recommendations, this is if we did what Al Gore recommended. This is the highly mitigated scenario. And again, we get a certain amount of warming, but then we get our act together, and it levels off, and we have a nice, consistent future. Here's the highly mitigated, just plain old mitigated, where we reduce our emissions a certain amount, and again, we achieve that nice level where we don't have any more global warming. And then this is business as usual. Okay, so this is what we're doing right now. We have not successfully been reducing our carbon emissions. Every year we release more and more and more, and that's the scenario where you end up with a lot more heat in the atmosphere. So these acronyms are the names of the global climate models. On a pop quiz, I would probably get about half of them right. But the first three letters are the name of the laboratory that made the model. And then whether it's an 8.5 or an A2, that's telling me, because I know these codes, this is business as usual. Okay, the blues are all partially mitigated, the greens are very mitigated, and that blue is the super mitigated. So I'm not going to try to get you to remember any of these. I'm just going to talk about mitigated. I'm really going to just talk about mitigated and business as usual moving forward. But that's the first uncertainty, right, about looking at the future. How well are we going to get our act together? Are we going to get together a lot, or are we going to just keep doing what we're doing? So when I'm trying to do projections for our local community, I have to cover that range, right? Ranges of emissions scenario. We'll change the answer. So in terms of the Bay Area, why did I put this climate dice into the title? Well, there was a terrific paper that came out by a NASA scientist in 2012 trying to explain to people this business, this science of trying to project the future. I'm not saying predict. I'm going to say project. And he says it's like God has dice, and every year he's rolling the dice. And I'll make him a he for now. And so just like when you're rolling the dice, last year doesn't control what happens next year. There's some inherent uncertainty from year to year because we have this very variable climate. However, the dice are now loaded. The dice are loaded to get us higher numbers. So even though we can't predict exactly what the dice is going to roll, we can predict this trend of higher numbers over time. And I'll just show you those plots on the left that I'm going to explain more in a little bit. Those are all those IPCC models for the Bay Area. Okay? Those are all the dice rolls moving forward of the trajectory that we could be on. So here's my incredible team. This is the Terrestrial Biodiversity Climate Change Collaborative. The Gordon and Betty Moore Foundation in 2010 asked, where is Dave? There, Dave Ackerley, my colleague who's at UC Berkeley, to handpick the people he thought would be the very best to think about Bay Area climate change. So we have oceanographers, we have climatologists, we have hydrologists, we have plant ecologists, we have wildlife ecologists, and we have these super duper spatial analysts and statisticians who know how to work with this data and who are making these maps. So this was incredible for Pepperwood because the month after we opened, we hosted this group and started the process of collaborating on this work. And it's really, if you're at the university, you tend to specialize and you only talk to other people in your specialty. And then you go to a conference, you get even more specialized. So if you write a paper and publish it, your like 4 best friends are reading that paper. Okay? Here we are getting the hydrologists to talk to the plant ecologists so that they can start to see the connections between their work. and getting the two different plant ecologists who have two different models to explain to the rest of us, what's the difference between your models, how do they work, and how could we come towards some consensus? So these folks come every year for an extended retreat at Pepperwood. We get our computers out and we geek out. And then we set a course for working together for the rest of the year. So we're really grateful. These are all the different agencies that are represented. We have government scientists from the U.S. Geologic Survey. We have the university scientists. The California Energy Commission has helped support some of this research. Point Blue Conservation Science in Petaluma, amazing partners. And we did all this work with the Bay Area Open Space Council as a partner, so that we had a very specific client who the Bay Area Open Space Council makes recommendations about which land should we save and how should we take care of it. So they had very specific questions they wanted us to help them with. So this is kind of my cartoon of our framework. And even though we want to get to the end of understanding where things can live, we decided we needed to do a very good job on this side of the equation. So if you think about how climate is going to affect us, the climate blows in off the coast, right? And it hits our mountain ranges. So you've got some combination of temperature and precipitation distributed over our landscape. Now, this part is changing, but thank heavens, at least this part is staying the same, right? Where the mountains are, where the valleys are, how deep the soils are, how receptive those soils are to receiving water. So we're able to do a watershed model. I'm going to talk a lot about this watershed model today that tells you where the water is going to end up. Blue is cooler and wetter. Red and yellow are drier. If you can't tell what this is right away, this is the Bay Area. Here's the Bay. These are all the different major watersheds of the Bay. So we start to capture, both understand the last 100 years of microclimates, and we can fast forward those based on our science. Then we start understanding where can the plants live. I'll talk a little bit about the vegetation modeling, but based on how the soil moisture is going to change, how might the plants change? And then you can finally start to ask this question of where can critters and people live? And I'd say we're about 75% along here, and now it's very interesting. At the Ecological Society of America, there are about 15 papers using the data I'm talking about today to start to answer these questions, to start to model where things are going to be able to live. So we got the opportunity, the group that I just showed you created this huge knowledge base, and last year, people in Sonoma, Napa, and Marin wrote a grant to the California Coastal Conservancy to use this database to answer real questions on the part of other agencies. So has anyone heard of the Regional Climate Protection Authority? Yeah? Okay. We've got one person who's an expert back here. So that is a really cutting-edge development in Sonoma County that they created one agency to talk to all the different county jurisdictions about climate. And they started out being almost exclusively focused on climate mitigation. How do we reduce our greenhouse gases? But people like me kept knocking at the door and say, hey, the county should be thinking about adaptation also. So they're our partner. And then the other agencies are the Sonoma County Water Agency, who are real leaders in this area, the Sonoma County Agricultural Protection Open Space District, and regional parks, and then all of the cities. So I'm going to be in charge of giving all of the cities climate projections that they can use for local planning. Then Mendocino County, half of the Russian River is in Mendocino County, so we're working with them, their water and flood district. And then the Napa Valley, we're dealing with them, the county planning, public works, and flood control agencies, and the Marin Municipal Water District. So this is just showing you a map of Sonoma. One of the messages we want is, it really makes sense to look at this as a regional issue. Okay, we share resources with our neighbors. The Russian River also provides water to Marin. So let's not just zoom in on one county, which is an artificial boundary, but look at the whole North Bay region as a whole. So the next part of the presentation is going to show you some of these preliminary results that we're working on. We're really in the thick of it right now of getting very specific answers from this data. We are the navigators of the data. We are the information brokers, and the agencies get to work directly with the scientists who made this data ask questions like, how long is it going to take for my reservoir to fill up? Or how much more fire danger might I experience in the lands that I'm managing? So this is the boundary. Again, I look at maps all the time. Here's the bay, San Pablo Bay. Here's Sonoma Valley, where we're sitting right up around there. Petaluma River. So this you're going to see this outline a few times, because once my mappers get this, they just map it. Because we've been working with the water agency for a while, the Russian River Basin, we're going to be doing monthly projections and daily projections. Okay? Daily projections for the next 100 years. Multiple scenarios. And they're going to run those scenarios to see how well their water system can survive it. These yellow areas, these guys are kind of new to the climate planning game. They're going to get monthly data, which is already a lot of data, like 1.6 terabytes of data for monthly data. So this is sort of the area as a whole and the level of effort we're doing in the modeling. So back to this question. Here's the global climate model of the IPCC. It's really called a global circulation model, and it models the atmosphere, right? Here's the Earth and here's the atmosphere, and it generates a very coarse map of projected climate change, 275 kilometer grid cells. So where we are, we've got 4 grid cells for all of Northern California. This is that too coarse, too broad brush kind of result that I was talking about. We do something called downscaling. I think we made that word up. But what it means is we shrink the pixels. So we go from this very coarse 12-kilometer grid cell. But wait, we can do better. So with our hydrologic models, we take that 12-kilometer data, and this is showing you the Sierra Nevada mountains and the Owens Valley and the Central Valley, just as an example. And we take it down to 270 meters pixel size. So everything I'm showing you today, yes. It's 270 kilometers on a side. So in the case of 270 meters on a side, each side is 270 meters, this makes an 18-acre pixel. So you can think about that as that each square we're dealing with is 18 acres, which starts to get to a pretty reasonable number, right? That starts to be at about the scale that I can use it for planting Pepperwood. It's going to show me the variation over Pepperwood. And what you can see is it starts to reveal the influence of the topography on the climate and hydro parameters. So back to the Bay Area futures. Here are all the models that the IPCC generated downscaled just to the Bay Area using that 12 kilometers. This one is annual maximum temperature, and this is time moving forward. This is historic from 80 to 2000. These are 30-year time steps. And this shows you the range of trajectories moving forward. Here's our super mitigated friend, where we get our act together unbelievably well. Here's our business as usual. And the models land in this range. All these are different dice throws, right? Rolling the dice, rolling the dice, rolling the dice. Well, guess what? This is rainfall. So here's historic rainfall. This is the amount of precipitation. This is more precipitation than normal going this way. This is less precipitation than normal going this way. And look at this. The models, almost half of them are getting wetter and almost half of them are getting drier. So I'm saying this is the big uncertainty. We don't really know how rainfall is going to behave. Is that because of emissions? You know, the variation here I explained is due to emissions. No, it's not due to emissions, because we don't really know how emissions are going to affect rainfall. We don't really know how the ocean currents are going to change. We don't really know what kind of cycles will be impacted. So there's real scientific uncertainty here, because research can't physically accurately predict exactly whether the warmer temperatures are going to put more water into the air or keep more water in a liquid state. So that's real scientific uncertainty. So we looked at this and we said, okay, how are we going to narrow this down? This is too many scenarios for a very practical person managing a water agency to think about, right? And maybe they don't need to think about that many different scenarios. How can we narrow down the number? Don't get overwhelmed, but this is how we narrow down the number. So one of our statisticians took all of those models and put them into what we call bins, or a cluster, right? The ones that are similar. And we looked at temperature as one parameter, but we also looked about, is it rainier in the fall? This is September, October, November precipitation. Is it rainier in the middle of the season, December, January, February precipitation, or is it rainier in the spring, March, April, May precipitation? And if you talk to the water agency, what they know is it's not just the total amount of rain we get, it's when we get it. So if we get a late storm in March, everything stays green longer, right? The reservoirs are not only full, but we don't need as much water to irrigate. But if we get that rain earlier in the season, it has a different impact. So we wanted to clarify that. So every time, these are bundles then of similar models that have similar characteristics and temperature and seasonal rainfall. And out of that bundle, we picked this guy. So this is how we reduced the number. We bundled them together and we picked one model to be representative. Okay? And our point is that statistically speaking, here's the cloud of all of those models. This is precipitation and maximum temperature. And this is how my guys think about these models. They think about them in climate space. Here's the gunshot of the gray of everything in the world, and here are the black dots, the ones that we said, you know what? We think this cloud of black dots covers the full range of those gray dots. So we can handle a smaller number of models. So we took those 76 models, we got down to 18, but guess what? I think 18 is still a few too many to deal with if you are the Sonoma County Water Agency. And this is where you start to have to work with the managers right away, because the science and the data you're going to use is part of what is your question, right? What is your question? If you're really worried about droughts, you're going to want that super dry scenario. If you're really worried about floods, you're going to want a super wet scenario. If you want something that's kind of middle of the road, you're going to want to know where the middle of the road is, right? So we wanted a reasonable number. We wanted realistic. Guess what? The water agency doesn't think it's very realistic that we're going to be super mitigated. But plus, if super mitigated happens, then we don't really have, we're basically just dealing with the conditions that we already know through history. But let's look at business as usual and mitigated, because we do want to look at more optimistic scenarios and scenarios that are more intense. The representative range, let's get the middle tendency and let's get the extremes. And then there was also this thing that the state of California is continuing to develop this work. So let's make sure we're using models that are consistent with the state and what the state's going to use going forward so we can compare. It's, what do I want to say? It's an institutional consideration. So here is the world of North Bay climates. So again, for me, this is just a big accomplishment that we even have very local data. Here is the historic average. And this is, again, getting wetter, going this direction, more precipitation. This is getting drier, going this direction, less precipitation. And this is moving forward in time. This is increases in temperature over time. Notice that I'm not giving you dates. I'm not saying in 2071, this is what we expect to happen. It's much easier to say, well, when we get to 2 degrees warming, then we think that these could be the impacts on our resources. We don't know when we're going to get to 2 degrees warming, but we have more confidence in telling you once we get there, what's that going to look like. So that's one of the things we're working on with people. But again, here are these scenarios. The center is the average relative to the amount of change to historic. The crosshairs is the amount of variability. So that's just an average, but what's that variability? And what it lets us do is say, what our managers end up saying is, yes, I want this really wet scenario. This is 40% more precipitation than the previous 100 years, but it's also 4 degrees warmer. And I want this very dry scenario. This is almost 20% less precipitation than historic and very warm. So these are our outliers. These are the extreme conditions. And here's the one that if your boss says, well, can you pick one that's kind of close to the middle? So we have sort of an average representative. We pick this model. This crosshairs right in the middle is the average of all of these guys. But again, we can't average these models and have them make any sense. They only make sense one at a time, which is why we're stuck kind of looking at them one at a time to get the range of things. But what we use that middle crosshairs to do is you say, okay, well, all these guys are hotter and wetter in terms of precip than average. All these guys are hotter and drier. And we call these guys the warmer wet ones. These are the ones that are mitigated, and the warmer dry. So this took about 3 hours. I had 22 managers in the room, and we had to come to consensus because I said, look, we're only doing this part once, guys. And this now is the regional database that we will have for the years moving forward to plan. And these scenarios with the circles on them will be available to everyone in our area to use. And so it's scientifically informed that it covers the whole range of IPCC models, but then it's also informed by the manager's priorities, what they want to work on, what they think is realistic. There's still some subjectivity here, I guess is part of my point, but we're doing our best. So if you did want, and most people do want to understand, this is the time series, back to the time series, this is just 4 of those models, but here we now have a Russian River basin projection that's specific to the Russian River. Here's historic over time. That 1 degree C, again, Celsius temperature increase is what we've observed from weather stations around the Russian River. And here's moving forward. Here's our business as usual scenario. It's getting warmer a little faster, up to 4 degrees C more. And then our mitigated scenario, cutting that in about half. So if we do a good job in mitigation, it'll be half as warm. The warming will be half as much. But here's that rainfall plot again. We have the wet scenario. Look at that. That's almost 950 millimeters of rain. That's more rain than we've ever seen in the historic record. Look at that. 500 millimeters of rain, less than we've seen in the historic record. By the way, this is the Dust Bowl of 1930. Okay? So we're looking at extremes. And so what I can tell you is I don't know exactly what rainfall is going to do, but it is likely to be much more variable. And we're going to see more extremes. Sound familiar? Like this year and last year? Really big storms and then dry periods? This is what the models are predicting. Now, some people might say, 4 degrees Celsius, that's 7 degrees Fahrenheit. Today it's going to be 72 degrees. So it'll be 79 degrees, but it's still, not so bad. But the thing is, these averages, these are long-term averages over 30 years. They hide the real variability. So this is a model showing you, on average at Pepperwood, we were getting 4 days above 95 degrees. That's what that dashed line is. And it's going up and down, up and down. But if this model goes forward with this average warming, we actually end up getting 60 days above 95 degrees. Okay? That's 15 times as many extreme days during our summer than we're used to. So that's where I don't want to sugarcoat and say we can handle these impacts. These are going to be pretty extreme impacts for people, for landscapes. And this is a good example. This is one of our hotter scenarios. This is a good motivation for mitigating, right? Let's not have this experience. So I told you that we wanted to concentrate on our water cycle. If you are a earth science nerd, I can give you a paper. It explains all the different things that go into it. But basically, there's evapotranspiration. There's the recharge that goes into the ground. There's the runoff that fills our reservoirs and our streams. And this model estimates the amount of all of those things for every 18 acres in the North Bay for 6 scenarios moving forward every month or daily based on where you are in that map. And one of the things we come up with is something called climatic water deficit that I'm going to explain to you. So here, for example, is the map of the basin. Again, here's the bay, here's Sonoma Valley, here's Marin, this is the Russian River part of Mendocino. And it's showing just how we can map these attributes over time. So this is temperature moving forward in July, the maximum temperature that we'd see in July. And one of these things that's counterintuitive is, I think when people think about climate change, they say, well, if you want to cool off, you head north or you climb the mountain. But not in the Bay Area. At this scale, if you want to cool off, you go to the coast, right? Because the coast is cool. And it's our inland valleys that are going to see more warming because luckily the coast will still have some air conditioning on it. And it's actually the northern part of our study area that's going to warm up the most. These are the towns of Cloverdale, Ukiah. These are places that are already having some pretty extreme water situations. Here is the rainfall patterns. This is one of those drier models where rainfall goes down. And one of the neat things about these maps is that even if you just look at the historical, you start to appreciate the variability of these climates in our region, right? We have very high rainfall areas in the Sonoma Mountains. We have much drier rainfall down near the bays and the valleys. But this is projected in many of the scenarios to reduce over time. But this gives us the opportunity to share this projection with people who will be impacted. So the model basically takes the topography and runs the water and the energy through the whole cycle. And this is why I like physics, because we have a pretty good handle on conservation of mass, conservation of energy, and how to make this work. And if you're really into the nerdiness of it, the model builds a cross-section of the landscape, and it knows how deep the soil is, it knows how deep the bedrock is, it knows how permeable it is, so that we can put the precipitation and the temperature in and then get these things back out. Basin discharge is how we check that we got the right answer. I'm going to show you what that means in a second. So this is stream flow on the Russian River in Hopland in total discharge per day. The blue is the observed, the red is our model. So this is how we make sure that the model is really representing reality. We compare it to an empirical record. We're not talking about a computer model anymore. We're talking about empirical science. So when I saw these scientists present this, I came to them with my card, and I want to work with you. I want to bring you to the North Bay. So here's their model. They're doing this whole model for the Russian River that's looking at all the inputs and the outputs, and then we double check against the historic record to make sure that the model is working well, and then we can fast forward it. So here's some of the fast forwarding. Here's historic flows on the Russian River at Hopland. Here are some projected flows. So again, it becomes very meaningful for the water manager to see the range of scenarios that they could have these very floody periods or this extended drought period. It's something the engineers can relate to. And here we're showing what we're calling a drought. And again, you can start to look at the frequency of droughts happening on the Russian. So climatic water deficit is a very important term that we didn't discover it, but we figured out how to calculate it. And it is a measure of drought stress. It's a measure of how dry, how arid the landscape is going to get. In this map, you're seeing that water stress, drought stress, is again in the coast. It's not very high, but you get to these inland valleys and you start to have more stress. If you are into this kind of thing, this is the rainfall coming in. This is evapotranspiration, drying out. And this climatic water deficit term is actually, you can graph it like this. This is the water the plant wishes it had. This is potential evapotranspiration. You calculate that as if you just have a bucket of water that can infinitely evaporate. This actual is constrained by what's in the soil. So that's why the model is so powerful. It's tracking the water in the soil, which is not a very large amount of water, but it's the water that most of us rely on. So we're able to start to say, where are the parts of the landscape that will be drought stressed? Everything this model does is in millimeters of water per year. So this, when you get 950 millimeters of water, that's 950 millimeters of water, which is about, let's say 250 is an inch. So we got several inches of water, several inches of rain the landscape wishes it had. What got us really excited with our ecologists is, look at this. This is the map of climatic water deficit in the South Bay. This is the map of the vegetation in the South Bay, where the dark green is oaks and the paler beige is the grasslands. So for those people who've been thinking, why do oaks grow in some places and grass grows in the other place? You can see that pattern in the landscape. What is that? What drives that? Here it is. And this is why our ecologists are over the moon right now. We have this tool that really helps influence, it helps determine and estimate where plants can survive. So this is showing, again, let's just say local. This is actually real change that we've estimated between 51 to 80 to 81 to 2010. So just with that 1 degree C warming that we've experienced and measured, we're talking about up to 20 millimeters a year of water that the landscape wishes it has. So, that's an inch or so, but that starts to add up, and these are areas, the red is places where that deficit has gone up. Now, interestingly, there are blue places where the deficit went down. Deficit going down means it actually got wetter over this time period. So again, it's a variable impact, but this is why you don't want to generalize, right? You don't want to say, oh, it's going to turn out this way. It's going to play out differently across the landscape. So climatic water deficit is the water the plant wishes it had. That applies to my oak tree. It applies to Farmer John's grapes or Farmer John's apples. So this is an estimate using climatic water deficit of how much more water may be needed for irrigation in the Russian River Basin. This is irrigation demand in acre feet per year, and here's the year. So we're able to use this stuff to tell the water agency, just based on the temperatures, how much more water might you be asked to deliver, or to say to the farmer, how much more efficient does your system need to get? We can then ask this about vegetation, and this is a big piece that we're working on right now. How might our forests and grasslands change over time? And of course, that really depends whether we're in that drier scenario or the wetter scenario, but the overall trajectory is that we will have less forests and more shrubs. We don't really know about the grass. Remember Santa Barbara County? Less forests, more shrubs. That's the trajectory we're on. And you can zoom in and say, for the redwoods, what water deficit do they like? As you can imagine, they don't like super dry areas. So we can say, here's the distribution of water deficits that they can tolerate. These are very low deficits, so they're nice and wet. These are sort of smack in the middle of the range. And this red part, these are the redwoods that are probably going to be impacted by climate change. They're already at the edge of what they can tolerate in terms of drought. And we can look at the historic distribution of redwoods. Everything in red, yellow, or blue is where redwoods grow and what their drought stress is. And we can fast forward it and start to say, wow, these guys are really going to be at the edge of their range. These guys actually are still doing pretty well, the blue and the yellow. So if you were buying a piece of land because you loved redwoods, you might want this information. Where are the redwoods likely to survive over the next centuries? Interestingly enough, grapes also are sensitive to temperature, rainfall, and water deficit. This colored map up above is showing you from 71 to 2000 where you can grow Pinot and Chard. The blue means they might ripen a little late. The warmer temperatures mean they ripen a little earlier. That's what this is. So just in the last 30 years, where you can grow Pinot and Chard has changed. And it's, again, moving towards the coast. Two implications. If you own a vineyard, you might have new places that you want to invest in for growing grapes. If you own a vineyard here, your grapes might be starting to get a little stressed. If you are Save the Redwoods, there are places that you didn't think you had to worry about vineyards coming that might be headed your way. That land's going to be more valuable. It's going to be not something you can assume is just going to stay in a forest. So fire. Climatic water deficit ends up being a great projector of fire. And obviously, people who manage forests and land care about fire. The people who manage your water also care about fire. Right? Marin Municipal Water District manages 17,000 acres for their reservoirs. Fire is not the friendliest thing for running a reservoir. It causes erosion. It reduces the quality of your flow. So this is something we're focusing on. Our models are still rather coarse, but you talk about the probability of burning 2 or more times. And you can see right now that that's pretty low. There's about a 0.1 chance in our area that this is going to burn, but it's going to get higher, like a 30% chance of burning within a 30-year period. Santa Barbara County, right? We've got higher rates of return intervals. And then, so return intervals, the other way to talk about it, how often are those fires coming? So some places now are projected to burn every 200 years, but those places might start burning twice as fast. So it's something we really have to be prepared for. Now, I've talked about all of these models, and I'm actually not a modeler, I'm a measurer. And I think our best strategy for being ready for climate is measuring the climate in real time, understanding what those impacts are, which of those scenarios is turning out to be more realistic. One way to think about it, out of these range of scenarios. So this is my preserve manager, Michael Galogli, and one of our incredible volunteers who retired from Agilent and came to me and said, I want to get you a weather station. Yes, I want a weather station. We now have 5. Dave manages all the software for it. But we're measuring the weather and the biology in the same place, which is kind of rare. We're looking at climate, we're looking at water, we're looking at how the plants respond, we're looking at how the wildlife responds. This is an outline of the preserve, and every single one of those symbols is a long-term monitoring location. We're measuring the water flow, the soil moisture, the weather. These are grassland plots. These are the woody vegetation plots I mentioned. We have 50 long-term forest plots, and these red cameras are wildlife cameras. So we want to collect this information now moving forward for the next century so we understand these patterns. And we host the university professors and grad students to come utilize this data so that they can advance the state of the science. It's pretty practical information. Our Sentinel site has only really been functioning for about 3 years. The water agency used our soil moisture plots to ask that question: how much of the rain is going to go into the soil before it hits our reservoirs? So they get a more realistic estimate of how much rain they needed. We were able to publish what plants were more stressed by this year's drought and which ones were more resilient. And it kind of goes on and on. The one thing I didn't have time to talk about today is we have a cutting-edge fog project where we're measuring fog at Pepperwood and looking at the patterns in the landscape, because that's a big unknown. So the take-home is, again, here's my temperature increasing over time. Here's the landscape getting more arid or drier. I'm just using 4 scenarios right now, but here's the business as usual scenarios, and here's the B1 scenarios. And if you start to squint, you're seeing kind of a trajectory that's pretty consistent. So we know that our landscape is drying out. The uncertainty is about how quickly this will happen and how far we're going to go along this trajectory, which will be a function of both how we mitigate and how our planet responds. So, just trying to get to the basics. We're trying to use this science to get to some pretty practical questions, these kinds of questions. How much hotter would it be? How much drier might it be? How much more flooding might we have as a starting point for planning for our county? And then here's all the places this information can go. So I'm not a big advocate of we need a climate adaptation plan. Climate adaptation is not something really new or different. Climate adaptation is good long-term planning. And so instead of having a climate adaptation plan, we really need to bring climate into every single one of these kinds of projects that we're already doing. And that's what the database of North Bay Climate Ready is going to enable us to do. We do have fact sheets. If you want to learn more about this, you go to northbayclimate.org. And we've developed these 4-page fact sheets to try to summarize what I tried to summarize in the last hour. I'm really curious. If you guys are interested, I can tell you more about how to get a hold of them. We have put the 4 scenarios I presented are on a web tool, and we're offering it to people. Here's Buckeye Ranch, formerly known as Preservation Ranch. You can put in the outline of your property and get those projections out, okay? And you can find out things like, wow, Buckeye Ranch is generating 14,000 acre-feet of runoff and 30,000 acre-feet of recharge of our drinking water a year. It starts to help the decision makers have a basis for making these investments. And what we're learning is investing and protecting our land is actually a great strategy for resilience. If you want all the data, it's published and online via our partners at Point Blue. And we haven't advertised this yet. I'm not sure how many people can really handle this, but we're getting these downloads where people are finding the data and starting to use it. And that's our goal, is to get the data into users' hands. So just wrapping up, when I talk about the environment, it's not just a specialty topic. You know what I mean? It's not a subset of what we do. When I think about the environment, I'm thinking about our quality of life. I'm thinking about everything that we enjoy in Sonoma that makes it such an incredible place for all of us to live. And this is stretching it a little bit perhaps, but I like to share with people, the future of nature is in our hands. We're in a part of the country where people and nature are deeply entwined. So we need to work together and maybe even get some lessons from the folks who are managing this place sustainably for the 14,000 years before we got here. And that's it. 2 things. There's going to be, if you're really interested in this topic, my partners are holding a forum, a North Bay Climate Forum on April 8th. Okay? And I can get the information to you all. And then if you want to come visit Pepperwood, April 26th, Sunday, we'll be having an open house, and you can come up, play, bring a picnic, go for a hike, and see some of our work. And that's it for the formal presentation. Questions?
Have, contrary to all the good things you've said, have any manufacturers, let's say of cleaning material or perfumes or something, come to you and complain that they don't want you making negative requests regarding their products? And I just wonder if that happens.
So the question is, are there people in the manufacturing sector who are making different products, perhaps that have greenhouse gas emissions, you're thinking? And are they not wanting this information to be out there? And I guess what I would have to say, at least in this part of the country, I think we've turned a corner where even the most hardcore business person realizes this is something they're going to have to take into account. So we haven't had people react negatively to sharing the message. There's a whole bunch of people working in, I don't know if you go to the chamber meetings or the Sonoma County Alliance of Business People, but they're realizing that recycling water and reducing their carbon footprints can save them money. Because those emissions are resources that are getting wasted into the environment. So recapturing water and recapturing carbon is actually becoming a sound business practice that more and more leaders in the business community are testing this out and then showing other folks in their community how they can make it work for them. So, yes?
You've made a very powerful argument about the necessity of mitigation. Now, the only two energy sources that don't give CO2 off are hydroelectric and nuclear. And the rest of the world is going like mad, building dams and nuclear power plants. In this country, it's been business as usual. Do you see any chance that that's going to change?
Now, do you think of solar as a non-emitting and wind? So I do think it's changing. Let's start with Sonoma County. We've got the Sonoma County Clean Power Initiative. We're very lucky that we have geothermal energy that you didn't mention, but geothermal does not have emissions except in the transmission, and then solar. So I think really tapping out our ability to use solar is going to be huge. That's not a simple solution because on the environmental side, there are impacts of solar arrays. I'm with you on the hydroelectric. There can be impacts of putting in hydro and using dams. On the other hand, we have a lot of hydro, so we might as well go ahead and use it. And I do have to tell you, I don't know where I am on the nuclear issue. I think a lot of people in the environmental community are going to be re-examining nuclear because of global climate change. But we've still got a very difficult disposal, demand for the waste. So I think the country is shifting, but I think there's a lot of industry and economic power behind the business as usual scenario. I think about it like this. It's like if you put cookies in a cookie jar and you leave those cookies in front of a bunch of kids and walk away, are they going to be able to leave those cookies in the jar? Because we're basically going to have to not burn oil and coal that's sitting in that cookie jar. And how do you create the incentives to start using these renewable resources that might be harder to access? They're not as accessible. How do we get those in the cookie jar so the kids can choose the better cookie? But it's a huge problem that luckily many people are working on, but I don't think there's a simple solution. But I think, again, locally, we've already made a commitment to clean energy, and locally we're figuring out how much of our energy portfolio can be clean. And you should look it up, the Sonoma County Clean Power Initiative. It's turning out to be cheaper than the traditional energy, the portfolio they have right now. So that, to me, is a bright sign. Yeah. Yes.
I know that the open space and Pepperwood and other places that control their land are interested in not preserving it necessarily, but adapting it and managing it to meet future projections. But a lot of land is owned by individuals who are interested either in preservation or development of that land to meet their personal objectives. As a result, population projections have a lot to do with what we can expect. How many of your models take into account birth rate, internal migration, and immigration as factors?
Yeah, so the work I showed you today has no social or economic modeling involved with it. It's just trying to model the climate and the hydro response. However, I think that's a critical next step, that we start to look at those questions. I can tell you that in Sonoma County, there's a lot of private property owners that are coming to our forums and wanting this information. We want to make this information available to them. But I think you've got a great point. if the state of California wants to cool off, a lot of people are going to want to move here. And that's why it's so important we have this dialogue now about what do we think is the appropriate land use scenario here? Where do we want to concentrate that development for new housing? So I think it's not an easy solution. It's one that's going to take us using those processes to come up with guidelines and be prepared for the fact that we may have a lot more people trying to move to Sonoma in the decades to come. Yeah.
I have a question about sea level rise. Are you looking at that at all, and thinking especially of the South County?
I'm very glad you mentioned that. I did not put my sea level rise slide up there. So sea level rise, there's been a lot of work done on sea level rise. The USGS has a dynamic model that they developed, the Bay Conservation Development Commission. There's a project called Our Coast, Our Future, which is kind of the sister plan to us. And they actually have tools where you can look at the sea level rise estimates. So people are doing a great job on sea level rise, and that's definitely part of the equation here. And the county-wide project that we're doing will include sea level rise. The Permit Resource Management Division of the county is in charge of what we call the local coastal plan, and that is the plan that will be incorporating sea level rise, and they are working on that on a parallel track with this project right now. So they're working on the coast and the bay, and we're working more inland. Now, the answer about San Pablo Bay, and sometimes I have extra slides that I would show. We drained the wetlands of San Pablo Bay. So what I'll tell you is my broad brush responses is sea level rise is going to take back those marshy areas. It is going to try to take them back, and we have to decide how hard we're going to try to keep that water out. There are risks for groundwater in Sonoma Valley. I live in one of these areas that could be, if the salt water comes up, there could be more saltwater intrusion. But sea level rise is not, because of the way the hills pop right out of the valley, it's not going to go a lot further than that super flat area between like 121 and 37. That's where most of the impacts are going to be felt. Yeah. Who has the microphone?
Lisa, thank you very much for a most interesting presentation, and indeed I support your work 100-fold. And it's a great pleasure to meet a fellow geomorphologist.
Oh, excellent.
I'm also a geospatial analyst. And a lot of the information presented here is data-driven and clearly deserves a lot of consideration. However, I might comment that I think that certain of the models that are presented have fatal flaws. For example, carbon dioxide in the atmosphere. They calculate that when Mount Pinatubo erupted, it put more carbon dioxide into the atmosphere than man has imparted over 2,000 years. Likewise, when that volcano went off in Iceland a short while ago, it put out enough carbon dioxide equivalent to that of the entire Industrial Revolution. The other factor that we are not taking into consideration, and of course Iceland is on the Mid-Atlantic Ridge.
Yes.
45,000 miles worth of sub-oceanic volcanoes, all of which we don't know where they're erupting, but they're all emitting carbon dioxide. Likewise, the other term that I haven't heard mentioned is geothermal gradient. That also is emitting temperature, heat into space. So I think we need to be a little bit more, what's the right term, considerate that perhaps anthropogenic global warming is not all human-driven. It's not anthropogenic. If you look at the history of the planet, going back 600 million, 1 billion, 2 billion, even since we had an atmosphere, in fact. If you look at our period of time, we are like a fraction of a second. So while we're talking about climate change, if I was Gaia, I would say we're probably talking about weather. And as we know, weather varies from day to day, from second to second. So I think that we should factor some of these considerations into the equations. Thank you.
Yeah. Well, I appreciate that comment, and I think it points to the complexity of trying to project carbon, which luckily isn't our job. That's the IPCC's work of doing those climate projections. And I would just say it's definitely true that volcanoes and et cetera are a natural source of carbon emissions. However, we also know that we have been an emitter of emissions on top of that. So you have to think about the natural cycles with our cycle on top. And in that short sliver of time of human history, we have doubled the atmospheric CO2 concentrations, in part because of our contributions. So I think you get to a good point. There's perhaps multiple causes of these patterns, but the pattern is here, and that's the one that we'll be living with. And that's in terms of the history of the planet, that's the most rapid increase in CO2 in the atmosphere. So one of the things I like working on climate adaptation is, regardless of the cause that we can have about this, the impacts are playing out and they're here. And that's why we want to measure them in real time, so that we can start to have that empirical basis for making decisions and not rely on models, So, yeah.
1,000 years ago, there was another global warming. And I don't think we had a Pepperwood or scientist working on mitigation nor on adaptation. Mm-hmm. But it did go away by itself after 200 years.
That's a great point.
Yeah.
So this is where I defer to my colleagues at Berkeley. They're actually doing a global change project where they're using things like lake cores. They're doing a core of Lake County. What is the lake there? Clear Lake. So, or you go and you start looking at tree rings, or you go and you look at the concentration of CO2 in ice bubbles in the Arctic that are very, very old, and you create this longer record going back to understand. But my understanding is still we are at this warmer end and rapidly changing, more rapid than anything we've experienced before.
You have done a super job on taking a worldwide macro problem and reducing it to the micro level at Pepperwood, Sonoma County. But I present a challenge to you.
Okay.
Your very intelligent group has to realize, in order to sell this, starting at the city council level, the state assembly level, and finally at the national level, you have to get a talk that they understand and can act on. And I can tell you, having tried to sell exotic weapons systems, we had to bring the scientists in and say, before you go to Congress, simplify it, make it understood, and then you'll get action that I hope you get. But congratulations on what you're doing.
Thank you. Well, and for me, that's the perfect closing comment, because I want to thank all of you for paying attention for an hour solid to this very data and science-heavy presentation. But the commenter is absolutely correct. I often have to give this talk in 10 minutes, sometimes 8, sometimes 7, okay? Which means I don't give all the graphs. I don't show the maps. I boil it down, and I'm learning how to do that. I wasn't kidding when I'm saying it's unlearning my scientific training to give that presentation to the decision makers that they can respond to. Luckily, I have a little experience doing that in my past, too. So that's really the conundrum. I think you hit it right in the head. How do you take this story that I felt very confident when Virginia said, you have a whole hour to explain this? I was like, that's great. We'll dive deep. And you guys have an attention span, which is much deeper than most of my audiences. But that point of the decision maker, they want to get to the answer. And that's why I think the work that we're doing to get them a very specific answer, they want an answer relative to their reservoir. They want an answer relative to this decision they need to make right now. And we got to get that specific, and we got to get cut to it. And I just appreciate that, and I take that challenge on. That's what we're going to be doing.
Thank you, Dr. Lisa McKelly, for your wonderful presentation. We hope you'll join